Okay, so question 3 is intermolecular forces with organic. And here they have a graph. They really like adding graph questions to your exams. But anyway, here's a graph, and as usual, the first question is a definition. The boiling point. This one is a bit of a ragey definition. It's not a point. The boiling point is not a point. The boiling point of water is 100 degrees Celsius. That is not a point. It's not a coordinate. The boiling point is not a point. It is a temperature at which the vapor pressure is equal to the atmospheric pressure. Nothing about equilibrium, nothing about equivalent, nothing about, what is the other one that they say? Nothing about equilibrium. It's equal. The vapor pressure is equal to the atmospheric pressure. Finished. You don't need to say whatever it is that Kevin Math and Science says. It's the temperature at which the vapor pressure is equal to the atmospheric pressure. Okay, that's all you need to say in order to get 2 marks. Then, for 3.2, they're doing a bit of an experiment, which is annoying, I suppose. They want the conclusion that can be made for curve P. Now, I haven't even read the question yet because I'm not very good. But anyway, the question says, the story says, the relationship between boiling point and molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. So there's curves P, Q, and R. So boiling point versus molecular mass. Those are the independent and the dependent variable. And then there's 3 different graphs. One of them is an aldehyde, one of them is a primary alcohol, and one of them is carboxylic acids. Sorry, it's a whole lot of them. So one of these graphs represents the aldehydes, which is a C double bond O on the end. One of these represents the acids. Oh, sorry, I must do another line. Sorry, come on, Terry. And one of them is the alcohols, primary alcohols, so it'll look like this. And then that will just be, there will be one carbon attached to that carbon. So each of these graphs, P, R, and S, one of them is, all of those are aldehydes, one of them, all of them are acids, and one of them, all of them are alcohols. They ask, what is the conclusion that can be made for curve P? This graph, well, all 3 of them actually, but P specifically, the relationship is directly proportional. So they are directly proportional. You get 1 out of 2. But the molecular mass is directly proportional to the boiling point. So the longer the carbon chain, the higher the boiling point. The molecular mass increases, the boiling point increases. The higher the molecular mass, the higher the boiling point. So now we've told you forever and ever that it's directly proportional or inversely proportional. Here, because they are not straight lines, so R is directly proportional. You can see that you could draw that line with a ruler. P is not directly, which is why here they're saying proportional rather than directly proportional. So they're only going to give you 1 mark for saying directly proportional because P is a curve and not a line drawn with a ruler. So the conclusion, if we want to avoid this whole do we say directly, do we not say directly, you simply write it out in words. The molecular mass increases, the boiling point increases. So as the molecular mass increases, the boiling point increases. We talk about the independent variable first, which is the one on the x-axis. I chose what the molecular masses were, and the molecular masses affected the boiling point. You choose the independent variable and you measure the dependent variable. And they say here, curve P, Q, and R are obtained, but I don't know whether you understand, they must have measured the boiling point. You can choose the molecular mass, you can choose how many carbons they're going to be, for example, but the boiling point you're going to have to measure with a thermometer. Then 3.3, they say explain the answer to question 3.2 in terms of the structures of the compounds. The bigger the molecular mass, the bigger the surface area. So when we're talking about the intermolecular forces argument, we're always arguing either strength, if it's different intermolecular forces, or size. So everything along this P line, everything on this P graph, all of them. So I mean, I know that they're going to be an acid, but if you didn't know, all of them are an acid, all of them are an aldehyde, or all of them are a primary alcohol. All of them. So even if you don't know your intermolecular forces, so say that you think that it has London forces, it doesn't really matter because all of them have London forces. So you're normally either arguing size or strength. If you have two different compounds which have two different intermolecular forces, the one will have stronger intermolecular forces than the other one. If you have the same compounds, so like in this case where they're all aldehydes, they're all acids, or they're all alcohols, whatever the intermolecular force is, it's the same for all of them. If they all have the same intermolecular force, why is the boiling point increasing? That is a size argument. So if the molecular mass increases, the size of the molecule increases, which means the surface area is bigger. So there are more sites for intermolecular forces to form, which means the boiling point will be higher. The more sites there are for the intermolecular forces, the stronger the intermolecular forces. So if there are different types of intermolecular force, you can just say that hydrogen bonding is stronger than London, or hydrogen bonding is stronger than dipole-dipole. But if they have the same, if everything involved has dipole-dipole, the bigger molecules have more sites for dipole-dipole intermolecular forces, which means that the intermolecular forces are stronger because there's more of them. So it's a subtle difference between each one-to-one being stronger and just the fact that you have so many, it acts as if it's stronger. Okay, so now for 3.4.1, they say that R is the alcohols. So the primary alcohols, this one is R. The red one, R, is the alcohols. They are asking which homologous series is represented by S. So I don't know whether you know, but alcohols have one site for hydrogen bonding. So their strength of intermolecular force is in the middle, in this case. Acids have two sites for hydrogen bonding. So if they're more or less the same sized molecule, acids will have double the number of sites for hydrogen bonding as alcohols will. So you could almost say that the strength would be double. Aldehydes do not have hydrogen bonding. Do you know hydrogen bonding only happens when you have an H bonded to a nitrogen, an oxygen, or a fluorine? So I just call it with my classes HNOF. But here what you see, there's an O with an H and there's an O with an H. So in the case of the acids and the alcohols, there's a hydrogen directly bonded to an oxygen, which means hydrogen bonding can occur between compounds or molecules of this nature. So between alcohol number 1 and alcohol number 2, you can form a hydrogen bond. Between acid number 1 and acid number 2, you can form two hydrogen bonds. But aldehydes do not have an OH. They don't have an NH and they don't have an FH. So aldehydes do not qualify to be hydrogen bonding. They are simply dipole-dipole. And dipole-dipole is a weaker intermolecular force than hydrogen bonding. So for 3.4.2, they ask you to refer to the strength. Curve S is the aldehydes. And if they ask you to refer to the strength, you need to compare S to R and P. So the aldehydes have dipole-dipole, and the acids and the alcohol have hydrogen bonding. So the aldehydes, or S, have the weakest or weaker intermolecular forces. It's the weakest out of the three of them. So therefore, they have the lowest or lower boiling points because you need less energy to overcome the intermolecular forces. They really don't like it when you say break. They always accept it, but you break a bond, you overcome an intermolecular force. If you want to do it properly, please don't say break. So for 3.4.2, why is the bottom graph the aldehydes? It's because the aldehydes, out of these three, have the weaker or weakest intermolecular forces, and so therefore they have the lowest boiling points, because lower energy is needed to overcome the intermolecular forces, which is why their boiling points are lower. Okay, so just to recap quickly, because I've now moved on to the next page, but anyway, these are the acids, these are the alcohols, and these are the aldehydes. So now the next question they're going to ask you to read off the graph. They say, what is the molecular mass of the compound with a boiling point of 97? So this is 50 and this is 100. So these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 10 blocks, so it's 10 blocks and they represent 50 degrees Celsius, which means each one of them is 5. I want 97, so this would be here, that would be 95. So I want the R graph that's at 97, it's going to be this one over here. So they are asking, what is the molecular mass of the compound with a boiling point of 97? It's that one over there, which sits on this line, which comes down here. On the x-axis, there are 10 blocks, which represent 20 grams per mole. So that means that it's 50, 52, 54, 56, 58, 60. It's 60 grams per mole. Sorry, I forgot to cover the answer. So they're asking you to read off the graph at 60 grams per mole. And then they ask for the IUPAC name of the compound in 3.5.1. It is going to be an alcohol. So you know it is going to have a C, an O, and an H. And the question is, how many extra carbons does it have? The C, the O, and the H are 12 plus 16 plus 1. It's the molecular masses of carbon, oxygen, and hydrogen, and that makes a total of 29, which means I have 31 left to add extra carbons. If I add an extra carbon, one extra carbon, then if I add another extra carbon, that's adding 24. Because carbons are 12. If I add 24, that means I have 7 left over. Because 31 minus 24 is 7. And so I add 1. So I add 1, 2, 3, 4, 5, 6, 7 hydrogens. So that, it has 1, 2, 3 carbons, 8 hydrogens, and 1 oxygen. And that number adds up to 60. So they are asking, what is the IUPAC name? It is a 3-carbon primary alcohol. The alcohol group is on the first carbon. It's propan 1-ol, or 1-propanol. You have to have the number 1 because you could have propan 2-ol. So I would suggest that we try and put in the numbers as much as possible. But propan 1-ol, because it could be propan 2-ol. For 3.6, they're now talking about A and B. A and B have a molecular mass of 74. A has a boiling point of 118 and B has a boiling point of 142. Explain the difference in these boiling points by referring to the structures of these compounds. So 74 would be around here if you want to try and get it from the graph. So 74 would be over there, and if I go through these, the one has a boiling point of 142, which is this bad boy over here, and the other one has a boiling point of 118, which is going to be that one over there. We are comparing an alcohol with an acid. Both of those have hydrogen bonding. Both of those molecules have hydrogen bonding. Carboxylic acids have London forces, dipole-dipole forces, and hydrogen bonding. And alcohols have one site for hydrogen bonding. So because carboxylic acids have 2 sites for hydrogen bonding, in addition to their London forces and dipole-dipole, alcohols have 1 site for hydrogen bonding with their London and their dipole-dipole. So the stuff in brackets you don't actually have to say. that means that the intermolecular forces in carboxylic acids are stronger, which means the boiling point is higher. B is a carboxylic acid, and A is an alcohol. So that's the recipe question, basically, for 3 marks in this case. You always talk about the intermolecular forces of them both. You talk about which one is stronger or which one is bigger. You talk about their size or their strength. Then you say that the one needs more or less energy to overcome, which is why the one's boiling point is lower or higher than the other one's. So you always talk about the same things with these kinds of questions: the intermolecular forces, the strength, the energy, and then whether the boiling points are higher or lower.